No, I can.
So, good. So welcome everyone to our meetup, to today's session, machine learning on the edge between industry and research. So first I want to thank our sponsors, which are Amazon and the SNT. They are both hiring, but please if you apply, make some reference to our group so that they have some metrics and knowing where the application comes from, what triggered it. Well, today we have two talks from researchers here at the SNT from the Sena Lab, so data management and services. So they're presenting the work they are doing with their industry partners. So the first speaker is Ramiro Camino, and he's going to talk about GANs, so generative adversarial networks. Thank you.
Well, hello everybody. Can you hear me in the back? Because the mic is just for the stream. Yes? First about me, just a bit about me. I come from Argentina. I got my master's degree in computer science in the University of Buenos Aires. I spent some time in the industry, and right now I'm a PhD student in here. And I'm working with anti-money laundering, fraud detection, anomaly detection, and right now deep learning. I want first to speak about the domain just a bit so I can describe how the data and the tasks that look like. So first about the data. Let's say I work with an industrial partner and we have data from financial institutions or banks or anything that can look like this, like transactions and account data. For example, for transactions, we usually have the amount of money, the currency, date and time, source and destinations, and a lot of categorical variables describing the transaction. And for accounts, usually we have, well, the name, sometimes the name is split between first name, last name, sometimes it's not, sometimes it's empty. We have a lot of other fields like the account type, date of birth, nationality, a lot of categorical variables too. What we do with this? Well, usually for fraud detection, for detecting suspicious transactions, there are a lot of approaches already in the domain. The most traditional way of detecting suspicious transactions is by rules. Rules crafted by experts, and the most common example is just check if a transaction is bigger than, let's say, 2,000 euros. That transaction is usually suspicious, not necessarily bad, but suspicious. Or we use machine learning approaches where we train models when we have labels, when we have examples of transactions that are suspicious or not. Or we apply anomaly detection approaches where we detect transactions that are different from the rest of the transactions. And the same thing for the suspicious accounts. We use rules too, we use machine learning too, but also what we can do with them is, well, group all the related transactions and create profiles about users, and we could compare profiles with other profiles, or we can detect sudden changes in a profile when, let's say, a user has a purchase that's very different from the amounts the user normally have. And about anti-money laundering, usually we work with several known patterns. For example, the first one, it's related to something called layering or smurfing, when, let's say, a criminal has some dirty money, wants to put that money into the banking system, but in order to avoid the checks and the known rules, splits the money, the transactions, into several transactions with a lot of intermediaries, and then the money is merged in a single account. That's one known pattern. Another pattern is, for example, a chain of transactions where every person in the middle, it's called like a mule or a smurf sometimes, takes a small amount of the transaction and sends the money to the next one, and everybody takes a small amount, and that's also related to money laundering usually. So all the approaches we take are sometimes related to graph mining, and sometimes regular, like traditional machine learning using features that somehow capture this kind of structure. But today I want to talk about all the challenges that we face, because I've been working with the things I just presented, but right now I'm working with other challenges. For example, the missing values we find when we work with data. Usually data is very dirty. We find things like, for example, I don't know, like in this example in the transaction I have a date but I don't have time. Sometimes I don't have a field is completely empty, like the type. Sometimes there are typos in the names. Sometimes there are invalid dates, like this account has a date of birth in the future. Or maybe, for example, the profession of this account is a PhD student. It's not between the valid values for the categorical values. And even if you think that, well, but nowadays you fill this with forms, and forms have validation, how can this happen? And it happens. Like there are clients that they deal with the things, and then we get this data, and we need to work with this data. And if we just discard all the dirty data, sometimes we lose a lot of information. So we need to deal with things like this. Another big problem we have is the extreme class imbalance. Usually, in any kind of fraud detection domain or subdomain, the amount of positive samples, the amount of, let's say, in this case, the frauds, are very small compared to the known frauds. And this can complicate a lot of things in machine learning. And sometimes we don't even have labels. So we cannot use supervised approaches. We cannot use the most common and most known algorithms. And another problem we also face is the data privacy. Sometimes we have some fields, like let's say censored, or we don't have the complete data, and sometimes we have only IDs for the accounts, for example. We only have the relationship between accounts, but we know nothing about the accounts. Or maybe we know this data, but we can't share anything. This is very common with banking data, so we cannot publish nothing about it. We cannot share our findings. Or the problem is sometimes we need to work inside a specific network or inside a specific machine without the resources that we need to work. So this was a bit of the introduction of the challenges we face. So the talk of today is how can we use generative models for this, and what are generative models? Well, I'm simplifying a lot in here, because you can do a lot more with generative models. But let's say they are models that take real data, and after training, you can generate more data that looks like the original data. This taxonomy was taken from the Ian Goodfellow's tutorial from last year. I recommend that you should watch it if you're interested in this subject. But I'm not going to explain all these models, and these are mostly related to computer vision, but I'm going to talk about GANs today, generative adversarial models, networks. So what can we do in our problem with these models? One thing is, for example, minority class oversampling. So in our case, we take the few samples we have from frauds, and we could try to synthesize more samples in order to improve the quality of our models, of our classifications or anomaly detection. Other thing we could do is data imputation, which is basically filling the blanks. For example, in this case, we could, based on the data we have from a sample, we could try to infer the missing data. So I don't know in here, like if you're familiar with neural networks, how they work. I mean, is in here someone who has no idea like how it works? I don't know, because well, I will just review a bit like the basics of neural networks, because there are some points that are important. Well, this is just a one-layer neural network where with the simplest architecture, where you take the input X or the features, you multiply by the weights, you add the bias, and then you apply some nonlinearity, some activation function. In this case, it's the sigmoid function. And you get the output or the prediction. In this case, it will be, because of the activation, it will be a real number between 0 and 1. And of course, this could be a lot more complex. There are a lot of activation functions. You could just concatenate several layers like this, and you will get a deep neural network. And there are a lot of architectures that I'm not going to show in here, like convolutions, recurrent neural networks, and so on. But the important thing is, you get some input, and after that, you apply all the things, and you get an output. And you want that output to be as similar as possible as your labels, your ground truth. Let's say, how do I measure that? Well, with a loss function, with some kind of error measure. In this case, it will be the binary cross entropy, where I measure how similar is the prediction to the labels I have. And how do I train it? What is training in this case? How do I learn something to improve in this task? I need to train, how I showed in here, the parameters. I need to change the weight and the bias. How do I do it? How do I do that? Well, thanks to all these frameworks we have nowadays, like, I don't know, TensorFlow, PyTorch, Theano, Caffe, when we in the forward propagation, when we calculate, let's say, from the inputs to the outputs to the loss, each operation is going to look something like this. I start with the weight and the inputs, then I add the bias and so on. And the thing is, thanks to these frameworks, I can calculate almost for free the gradients of these operations, because these frameworks already know how to calculate the derivatives of all these operations, and we get this for free. What we do with these gradients, well, basically there are a lot of optimization algorithms like stochastic gradient descent that helps us to understand in which direction we should update and we should move the weights. Okay? Well, then how do GANs work? GANs are look like this, and they are composed by two networks. One is called the generator, the other one is called the discriminator. People always describe this as a game between a counterfeiter and the police, where the generator tries to generate samples which are fake, and then the discriminators need to distinguish between the fake and real samples. How? Well, the generator takes some random noise as input, and then at the beginning it will generate just random samples. They won't look like the real samples. And the discriminator at the beginning also will be very bad at distinguishing between real and fake. But as we know already which is real and which is fake, we can use that as a label, and we could train the discriminator, and we can backpropagate all the gradients to the generator too in this way. So even if we don't have any labels, actual labels to the generator, we can backpropagate through the discriminator. And the loss, well, I'm simplifying a lot in here, but the loss in some way will try, it's an approximation of the Jensen divergence, Shan and Jensen divergence, or the KL divergence, which is a measure of how similar two distributions are. But what happens is that usually GANs are very popular in computer vision. This is a very popular example. where they trained with a lot of images from hotels, and they generated all these images. I don't know if you can distinguish from there, but all these images are fake. If you look very, very close, you will realize that they are surreal, but from far away they look like pretty real. So they are very popular right now. They are very good at generating images, and they can do a lot more in computer vision. But the thing is, this is a continuous space, and we deal not only with continuous variables in our domain, but also with discrete variables. As I showed before, like, for example, in a transaction, the currency is a discrete variable. But what's the problem? Okay, I will try to explain why that it's a problem. A very common use case for GANs right now with discrete samples is generating words. And when you generate a lot of words, you can generate text, but you generate word by word. You can also generate character by character, but in this case, let's say I take the 10,000 most used words from a data set, and I create a dictionary. I sort them by frequency, for example. And if I want to represent a word from that dictionary, I can just use a one-hot encoding. In this case, it will be a vector of 10,000 dimensions. They will be mostly zeros, and only the dimension corresponding to the word that I want to represent will be a 1. In this case, the third one, it's because I want to represent the word and. So I have a smaller example right now. Let's say I have only 4 dimensions. And let's say, okay, given the output of a neural network, the linear output of a neural network, I want to sample a discrete element from it. Usually you could use, as in any classification task in neural networks, you could use a softmax, which transforms this vector in the left to a distribution, which is just a vector that adds up to 1, and where each dimension is greater than 0. And a way of sampling something from that distribution is, for example, using the argmax, just taking the maximum value and this is the 1, not the 2, in fact, the second dimension. But what's the problem with this? That the sampling operation is not differentiable. So if I plug in this into a GAN, the softmax and the sampling, that could be an argmax or other ways of sampling, the backpropagation, let's say, gets blocked. So you can backpropagate to the generator, and you cannot make it learn anything. So how can you solve that problem? There are several approaches. I will show you at least 4, and I will try to explain you why they don't apply to my problem, and then I will try to solve it. The first approach is called MedGAN because it's related to healthcare. In this publication, I mentioned it in the bottom, they use 2 phases of training, separate phases. In the first phase, the pre-training, the authors take the real data and train an autoencoder, which is basically a pair of networks where the first one is called the encoder, and you can consider that the encoder is like a compressor, like somehow a model that reduces the dimensionality of the data. And then the second one is the opposite. And the output of this model is the reconstructed version of the real data. And you train this model by comparing the original data with the reconstructed one, and you want to minimize the difference. So at the end, you will get, in theory, a good compressor and decompressor of the data, or a good dimensionality reduction, or even a feature extractor. In this case, it's like a feature extractor, because in this model, the authors discard the encoder afterwards, and they put the decoder in between the generator and the discriminator. So you don't need to sample anything. Basically, the generator generates codes, which are continuous vectors, and then the decoder transforms the continuous vector into a discrete sample. And in this paper, the authors addressed let's say the multiple categorical variables, but just ignoring that structure, and the decoder only uses sigmoids. So each dimension is just considered as a binary feature, and they don't care about the structure. The thing is, sometimes they generate invalid samples, because they could generate more than 1 per one hot encoding, because they use separate sigmoids. So there are other approaches. This one is pretty similar, but this one alternates between steps. It doesn't have two separate training steps. In this case, the autoencoder is trained with the GAN at the same time, but in this case, the one that's used is the encoder. They take the real data, encode the data, and then the discriminator needs to distinguish between real and fake codes. So the discriminator works with continuous samples. It doesn't work with discrete samples anymore. And as I'm showing in there, it doesn't say discriminator, it says critic, and the loss is a bit different, but I don't want to describe a lot that. The thing is, they have another let's say, improvements that were presented in another paper called WGAN. It's just a better way of training. Okay, so these two approaches then use an autoencoder. There are other two approaches that try to deal with the sampling of discrete elements. In this case, this is just a regular GAN, but instead of putting a softmax in the middle, they use something called a Gumbel softmax, which uses something called the reparametrization trick that avoids this problem of the gradients being stopped. If I have time, I can explain this at the end, but I think it's maybe a lot of formulas. But the thing is, this special softmax can sample discrete elements. But in this paper, they were working with text, and they were only generating one categorical variable at a time, so they don't have multiple categorical variables. They were working with text. Text is basically only one very big categorical variable, like the element you pick from the dictionary. And the last approach is called WGAN with the gradient penalty. It's again, I'm showing again this critic and the strange loss. But the authors in this paper claim that thanks to this strange discriminator, you can train a GAN without sampling, just by using the output of a normal softmax. I mean, you will compare between real samples and distributions, but it seems that it doesn't matter, that they said it works. But again, the softmax only generates one categorical variable at a time, so it doesn't apply to all samples. So how can we solve that? I will show our approach and an example first, just to clarify the thing of multiple categorical variables. In this case, I'm just using two from the, let's say, a user account. The type of a user account could be a standard account, student account, I don't know, company account, and the country. I have just some countries. And in this case, if I want to represent an account from a student and other country, I need to put two dimensions into one, not only one dimension. So this is like a multi-one-hot encoding. So that's why I was mentioning that only with one softmax or one Gumbel softmax, you cannot generate something like this. So we proposed this approach, which basically I will show how to apply it, but some of the models will be modified like this. After the output of the model, we split into parallel layers, where each layer has the size of the categorical variable we want to work with. And then after applying either a softmax or a Gumbel softmax, we concatenate all the outputs and we get only one output. For example, the two approaches with autoencoders, we need to modify the decoder in this way, using Gumbel softmax. For the one that was using Gumbel softmax, well, we modified the generator. And for the last one, we modified the generator too, but we don't use Gumbel softmax because they said that with the regular softmax, it works. Okay, so how do we know if what we're generating works? I mean, if the quality of our samples are good or not. In the case of the images, you can just look at them, basically. It's a very bad metric, but because you cannot validate all your samples just by looking at them, it's time-consuming, but you can do it. You can at least test somehow how it's working. It's the same if you work, for example, with sound, with music. If you work with text, somehow you can also evaluate by yourself. And there are also some domain-specific metrics. For example, for text, there are a lot, like you generate text and then you check if the grammar is correct or not. That's one way. Or there are a lot of readability measures to see if the text is easy to read. There are a lot of checks for structures. For example, there are papers that try to generate poems with a very specific structure. If the generated poem doesn't follow that structure, so it's wrong. The same with music. There are some papers trying to measure polyphony, but not like if it's bad or good, but at least to be the same as the original data, or scale consistency. But the thing is, all these metrics, they are not good by themselves. There is no metric that can be used by itself. Like, you always need more. It's not because your text has a correct grammar, it's enough. You need more metrics. And even I mentioned that the GANs somehow approximate the chiral divergence. So in the loss, you're already measuring if the generated data has a distribution that's similar to the original data. But there are a lot of papers proving that that's not enough. Sometimes in the numbers, you see that, well, these distributions should be very similar, but the quality of the samples is terrible. I mean, very surreal images and things that make no sense. There are a lot of papers explaining why. I could send the links afterwards, but in our case, we don't have these domain-specific metrics, and also we cannot just look at an account and generate an account or generate a transaction and say, yes, it looks good. It's very hard to define what looks good for a transaction. So, I can't see very well that plot. So what we did is we used this data set, which is called US Census from the 1990s. This data set is in the UCI repository. Why we chose this one? Because it's the biggest data set available with only categorical variables. It's pretty big. It has 2.5 million samples, something like that. And let me explain this plot, which is a bit complicated. I have three rows, one per metric, and I have 6 columns, which are, the first 2 are the baseline models, so original models that can be used, the decoder models. The other 2, I cannot use them because of the softmax limitation. I cannot generate multiple. And the other 4 are the modification of the original ones with our approach. And what are the metrics? Okay, so let's say the top left square is the adversarially regularized autoencoders model. In the x-axis, I'm just showing for the original data the proportion of ones per dimension. So it's basically the distribution, independent distribution of each feature. And the same for the sample data. So if they have the same proportion of ones, they should be in the diagonal, the points. If not, it looks like the 5th one. So this is only like, let's say, like a simple check. They should at least be similar dimension per dimension independently. The second one is trying to capture somehow the dependencies between the features, but it's a bit more complicated. So in the x-axis, again, it's related to the original data. The y-axis is related to the sample data. What we do is, this is proposed in the Medgan paper. We take dimension per dimension, it would separate that dimension. And we consider that that dimension is a target class, is the label, let's say. And we train with the rest. like we use the rest as features. So we try to predict the one that we separated, and of course we have tests and train, and then we test one classifier per dimension. So the metric that you're seeing there is the F1 score per dimension. And if they have the same predictive quality in the sample data and the original data, they should be in the diagonal. You don't want to have better prediction quality in the sample data because it means that you have more than dependencies that you should, that you're capturing things that don't exist. And the same if it's worse. So they should be similar. And the third approach is one that we propose because it's an adaptation to our case, is basically doing the same but separating one categorical variable at a time. So we train one predictive model per categorical variable. And in this case, we are using accuracy node F1 because it's multi-class. And well, in this case, for this data set, it seems that the best one is the last one in the 3 metrics. And we repeated the experiment with several data sets, one per block. And we can see, I don't know if you can see the bold numbers, but the thing is, in all the cases, the best model was always one of the 4 models with the modification in every metric. The only case that they were pretty close and that there were ties was the first case, because it was a case with very small categorical variables. Most of them were binary. So if they are binary, then the models using the sigmoids, they're the same, like as good as our models. As a conclusion, we can say that comparing with the 2 baseline models, usually, I mean, in all the cases, our models outperform, in all the metrics, those models. But, well, there is no better model in any case, which is reasonable. We cannot expect that one of the models is good for every data set. It doesn't happen usually. But at least from the 4 models that we propose, always one of those models is the best. But the thing is, well, this comes with a cost because sometimes you don't have that information, the size of each categorical variable. Sometimes you just receive the preprocessed data set which is only binary, and you don't know the limits of each one-hot encoding, let's say. So, well, it was half an hour. I hope, do you have any questions?
Yeah, I have a question.
Hmm?
So, there is some experience when you have a racing between, the generator and the discriminator.
Which, sorry?
Racing.
Yes. Well, this is, I will repeat the question for the streaming. He asked me if there is some problems with let's say, racing between the generator and the discriminator. Well, yes, and it's not something related to our models. It's in general for these kind of models, and it's very hard to. These models are very hard to train, and there is a lot of tuning and things that you can do. For example, is if there are a lot of symptoms. If the discriminator converges too fast, it's bad. The generator will never recover from that because they are playing against each other. If one of them wins too fast, that it doesn't mean that the quality of the generated samples will be good. It means that, okay, that's it. They will not learn anything else. So there are a lot of tricks. You can, for example, change the amount of training steps you have for the discriminator and the generator, because you need to train them by alternating steps. You can always increase one or decrease the other one. Or you can change the architectures or lower the capacity or the contrary. You can make one of them more powerful than the other. Sometimes it depends on the architecture, on the problem, but yes, and yeah, you need to experiment a lot. Yes, it's a common problem, yeah.
You can have, for example, identity some problems. For example, when you make some transaction and you have something that is fake,
Mm-hmm.
and I think it's a race. This is the race between the guys that are building some adversarial networks,
Mm-hmm.
and you you must preserve the security of the system. And
Yep.
I hope that will not come in the virus dilemma. we have today in the systems.
Yeah, there's a lot of, it's an iterative process, right? You need to always improve. And there, in fact, there is like a new topic, let's say. It's not new, but somehow now it's getting popularity. Adversarial models in general. There are a lot of models trained to beat another models and to, let's say, cheat them on purpose. Like trying to cheat virus detection software, you generate malware and they detect you and so on. Or models to generate images that can beat image recognition models. So you can print some patches that you can print a patch and put it on top of an image, and suddenly the model cannot recognize the image anymore, for example.
Maybe there can be a big problem in autonomous cars.
Yeah. And
autonomous objects and everything that.
If someone takes a sign and put it in front of you, maybe your self-driving car can, complicate things.
Yeah.
Another question?
It's more about like the data set you mentioned in the beginning, where so you have like transactions information, and you are approaching it like as a graph problem. Like I know that this transaction goes there, and then they converge. But my point is, I'm just curious to know, like, are you really able to get those? Because, for example, from the standpoint of a bank, like I see a very partial view of this graph,
yes,
where I do have accounts, and for the rest, like I just see a few lines, and all the rest is missing. Yeah.
I will repeat the question. If it's possible to get, let's say, a full view of the transactions, because usually it's true in banking data, sometimes you have if you can get some banking data, sometimes you have a partial view of the problem. And it's very hard to track that kind of circuits or patterns. Yes, it's true. Most of the papers in anti-money laundering rely on synthetic data and simulations, and the ones that claim that they are solving something, they cannot share the data, and so you don't know what they're doing. Anti-money laundering is a very tricky domain. Yeah. But yeah, it's true that if you only have partial information, you cannot just use graph techniques, let's say graph mining techniques. You need you put, I don't know, features instead of features like the amount of sends, the amount of receive. It's like putting the degrees of the graph as features, things like that. But yeah, it's complicated. Yes?
What kind of software are you using, and how much time does it take to train your model?
I'm using this very nice platform, the HPC. Yes, I'm currently working with PyTorch. And I'm using the HPC platform from Luxembourg because with my laptop it's impossible. I'm using PyTorch with GPUs. Usually, for example, for the census data set with 2.5 million samples, I'm not using them all because I'm splitting train and test. It takes maybe, I don't know, for the simplest models, maybe 1 hour to train with the GPUs. But it's not as terrible as working with computer vision because the dimensionality is, smaller. So at some point it's not that terrible, but still, with my laptop I can work. Any other questions? No, sorry.
Yeah, I also have a question. So just let me try to summarize it, make sure I got the presentation right. So you have an initial data set, and you're trying to extend this data set using adversarial network. So I presume that the problem comes from the size that the data set is too small on the start. So I was wondering whether that you were trying to create a classifier to detect whether or not there is money laundering. So I was wondering whether you tried then to train a classifier with the initial data set compared with the extended data set that you got out of your GAN network and see whether you could actually see performance.
Yes. Okay. So I will try to summarize. The question is if I'm working with comparing original data, the classification of the original data and the classification of the data augmented, let's say. Well, yes, I'm working with that right now. I didn't present that right now. I just, because I presented a lot of things, and I just showed you how to generate data and the problems. But yes, I didn't show you exactly how am I doing the data imputation and the data augmentation. And yes, I'm working with that right now. Comparing also with, not only with the original data and the augmented data, but also with other data augmentation techniques. I mean, the most popular one is SMOTE. But SMOTE is for continuous data. There are variations, like there's an algorithm called SMOTE NC, but it's not very good. There are other algorithms, but I'm comparing with my results against those algorithms and the original data without any augmentation. Also combining with undersampling, because it's not only about oversampling the minority class, but you can also undersample the majority class. So yes, I'm working with that right now.
In terms of percentage, is it can you augment your data? Is it really worth of us to give a try?
Well, for sure it's better than SMOTE. I can beat SMOTE very easily because SMOTE is prepared for continuous data. And only for a few, let's say, small decimals, I'm beating the original data. But as this is very hyperparameter dependent, I need to run a lot of models to see if I can fine-tune this a bit more. And also I could try with I showed 4 architectures, but there are 1 or 2 more I could try. So I'm working with that right now. But it looks promising. And well, my next step is the data imputation.
Okay, so let's thank the speaker. So the next talk is given by Mang Sing. Mang Sing Du, also PhD student with the Senan Lab here. And so you will be talking about real-time bidding and online advertisement. So, yes. Thank you.
So thank you everyone for coming here today. I'm a PhD student here at SNT, and my name is Manxing. And the topic of today's talk is real-time bidding-based online advertising in a nutshell. So today's talk, I would like to just walk you through the technical background of real-time bidding system. And hopefully after this talk, we can have a brief view of how a real-time bidding system works and some state-of-the-art algorithms being used by the industry to solve different challenges in this area. So here, there are so many research topics in this area. Here I only listed 3 of them because these 3 are the major tasks from the advertiser's point of view. So I will take step by step to show you how to build or how to design an optimal bidding strategy. So at first, let's take a look at some traditional advertising. So these are 2 photos taken in Tokyo and in Hong Kong. There are so many advertisements everywhere. By looking at them, I feel quite overwhelmed, and sometimes I cannot focus on any of them. And from the advertiser's point of view, they fail at targeting a specific kinds of audience. And also, as a customer, if I want to look for some information, it's also hard for me to find some advertisements I want to look at. So in the digital world, we want to do it in a more intelligent way, which is called computational advertising. So here we use some algorithms and try to optimally match the advertisers and the end users. So here, one type of the online advertising is called sponsored search. So in this case, every time you search something in Google, and the advertisers try to target the keywords in the search query. So here, for example, if I Google something about the flights. So the advertisements shown here are most relevant to the word I Googled. And I think, so the search engine always associates the advertisers with the keywords, but not with the end users. A second type of advertising is contextual advertising. So here, what it does is it tries to match the content of the web or the content of the video you're watching. So here, for example, I was watching some travel videos, and YouTube just recommended me to download Expedia app. And the third type of online advertising is display advertising. So here, the advertisers are trying to target your behavior. So for example, when I just read something on BBC, Booking just recommended me to book some hotel in London. It's just because I searched for hotels in London a few days ago. And so that's why it tracks my behavior online, and now it reminds me to finish my booking. So here is a report showing that right now the amount of money spent on digital display ads. For example, in US, last year there are over $32 billion spending on showing the ads online, and this number keeps growing. So by seeing such a huge money flow in this market, maybe we should make some better or more intelligent decision about how to spend this money and also optimize the profits. So here is how a real-time bidding system works. So every time when we open a web page or an app, so these two ad slots are sold in real time to the users. Once I open the browser will send a request to a place called Ad Exchange. So here, the Ad Exchange will hold a real-time ad auction, and the Ad Exchange distributes multiple bid requests to demand-side platforms to ask for an ad. And here I only show one DSP, but usually there are many. And so each DSP are bidding or trying to select advertisements from their ad inventory. So a multiple advertiser will register their ad campaign on this platform. And the DSP, on behalf of the advertisers, upon receiving one bid request, it will try to look for the best campaign to show to the user. And in the meantime, by getting, the information are coming from the bid request, and also the DSP can gather more user data from a third party called data management platform. And the demand-side platform will set a bid and send it back to the ad exchange. So the ad exchange, upon receiving all the bids, it will select the owner with the highest bid and show the advertisement from the winner to the user. And once the user clicks on the ad, it will be redirected to the winner's landing page. And on that page, maybe the user will purchase something or subscribe to a certain type of service. And then this kind of behavior will be sent back to the DSP as the feedback. And later on, the DSP can use this feedback to adjust their bidding functions. And everything happened here, what I've just described, should be within 100 milliseconds. So now let's take a look at a demand-side platform and how it works. So basically, there are two stages. One is offline and one is in real time. So there we we need to train models by using all the historical bidding requests. So here, the first thing we need to guess is whether this user is gonna click on something or buy something, which is click-through rate or conversion rate estimation. And a second model is winning price estimation, which means we need to guess once we can win this auction and how much we need to pay. And here, of course, every advertiser will have a budget limit. So you use all this information and then come up with a bidding function. And in real time, once we receive a bid request, we will first do something called data preprocessing. So maybe, for example, the advertisements are designed to be shown to a certain type of users, let's say only users from Luxembourg. So they have a few filters just to target a specific target a specific group of users. And also we need to set probably the frequency and recency of the advertisements, which means the same ads shouldn't be shown to the same type of user for multiple times within a short time period. And also the DSP can gather more information, use cookie matching to track the user's other online behavior from third-party agencies. And once we train a bidding function and we receive a bid request, we'll just use it to generate a bid price and send it back to the ad exchange. So now let's first take a look at user behavior prediction model. So here is the piece of information I can get from the bid request. So all of them are categorical features. So some of them are related to the users, for example, the region, city, and the country. And some features are associated with the ad exchange, and some features are associated with the publisher. So we need to use all this information and to predict whether there's a click or not. So the click-through rate is defined as the number of clicks divided by the number of impressions we want. And usually this click-through rate is very low, around 0.5%. So this is a very typical classification problem. And now I want to talk about feature representation, because all the information we have are categorical features. So a very popular way to transform the categorical features is one-hot encoding. So here, each unit here represents a specific value in our input. So the size of this one-hot encoded vector would be the sum of the unique feature values in the input. And after one-hot encoding, usually we will end up with having a very high dimensional binary vector. It can be up to 1 million binary features. And also this vector would be very sparse. And another way to transform or to encode the categorical features is called hashing. And in this way, we first just decide or define the encoded dimension. In this case, we can say the encoded dimension is 5, and we take a hashing function just to transform the text into an integer. And we take a modulo operation between the hashed integer and the encoded dimension. And we use the remainder as the index for the encoded vector. And in this way, the problem is that so different feature values may collapse in the same dimension, in the same unit. So later on, it's very hard to interpret it, the meaning of each unit. And also, even it gives us dimensionality reduction, but let's say sometimes for the same input, they will generate exactly the same encoded vector, which is called collision. So this hashing trick has not been widely used in the industry, I would say. And here are two categories of the models we can use to do CTR or CVR prediction. So one type is linear models, and the other type is nonlinear models. So the first we can look at logistic regression, which is very widely used by the industry, or is also very widely used to solve this binary classification problem. So here, X would be the input vector we got from the bit request, and also is already one-hot encoded. And we use the sigmoid function to get an output between 0 and 1. We can use that number as the click-through rate. And here is the cost function of the logistic regression. And to minimize this cost function, we use stochastic gradient descent. And here the problem is, because stochastic gradient descent, they use, every time they update the parameter, they only use one data sample. And the learning rate alpha is the same for all the feature values. And also it's very hard to control the learning rate. When we have a large learning rate, and you can see the loss would have oscillations. And if we use a very small learning rate, then it takes very long time to converge. So there's another framework proposed by Google. So it's an online learning framework just to accelerate the learning process of logistic regression. And here it makes sure that every update, the weight will not be too far away from the previous value. And also it introduced something called per coordinate learning rate, which means previously, because we have one learning rate for all the feature values, and now we have one learning rate per feature values. And in this way, it can make sure that the more frequent feature values will have the learning, and you can see the learning rate decrease more quickly. And there are some pros and cons for linear models. It's very easy to implement, and it's highly scalable, and you can do online learning. But the problem is it fails to capture the feature interactions. For example, maybe we have a user, an iPhone user, at specific time of the day, and his behavior is totally different, and he has more like higher rates or higher potential to click on something. So this kind of feature interaction cannot be learned by linear models. And now I think in the industry, they are moving towards to use nonlinear models. A very famous model is called factorization machines. So here what it does is, on top of the logistic regression model, it adds another term to capture the feature interactions. And here, xi and xj are two different feature values. And you may say that maybe we can use one single weight to measure this compound feature. But the problem is, if in the training data, iPhone and 8 p.m. Have never appeared in the training data, then that weight can never be trained. And what if in the test data you see this combination and you don't know how to do the prediction, and you don't know you don't have an optimal weight for this specific compound feature. So what it does, factorization machine does is it projects this one weights into a latent space. So it uses the inner products of two k-dimensional vector to estimate this one weight. And in this way, as long as iPhone and 8 p.m., these two feature values appear in the training set separately, so the weights can be trained and can be optimized during the training process. And so in this way, in the test set, when you see a new combination of feature values, it can use these two independent trained vector to approximate the weights. And one step further, there's another paper proposed field-aware factorization machines. So previously we have, for one feature values, we only have one latent vector. But here, for example, feature value is Windows. And for each field, which is, let's say, the feature name, browser, and country, so Windows will have two different vector for these two different features. So in this way, it makes the prediction, or it can learn the interaction between feature values in a more specific way. So this field-aware factorization machines, this model has been widely used in the industry. And even one step further, if we want to learn even more sophisticated correlations between feature values, we can, of course, use neural network. But the problem here is that if we use directly the one-hot encoded features, for example, here, if I have over 1 million binary features, and let's say I have 500 neurons at the first hidden layer, then we will end up with having 500 million parameters. And it's very hard to train such a huge model. So here, one paper, they try to use the weights learned by the factorization machine. They just use the parameters they add one layer of the weights taken from the factorization machine and then train the neural network. So in this way, they reduce the dimensionality of the input. And so here's is an example of the results. So AUC is the metric we use to measure the performance of the prediction model. And the left column indicates the campaign ID. And here the first column is the AUC of logistic regression and factorization machine. And the last one indicates the factorization machine-based neural network. So here you can see some improvements in terms of click-through rate prediction. But you would say maybe the improvements is not that much, around 0 point something %. But in real-time bidding or in the CTR prediction task, such improvement can be seen as a significant improve. And of course, there are more work in this area, and I couldn't cover all of them. So if you are interested, and you can find some references here. And there's one more thing I want to mention about training a CTR model, is we need to do unbiased training. So first, we assume that all the bid requests, they come from an unknown distribution, Px. So we just say the density function of the bid request looks like this blue distribution. So after this online auction, we will see some, we will win a parts of the auctions, and we will lose some of them. And for the winning auctions, we will have the labels indicating either clicks or not. But for the lost auctions, we don't have any labels, and we cannot use them for training. So usually when we train a CTR model, we always use the impressions. And so these data are coming from a different distribution, comparing with the bid requests. So the difference between these two distributions is the winning probability. Because for some bid requests, we set a bid price and we win some of them, and which gives us the distribution of the impressions. So during training, there's one trick to correct this unbiased data, which is called importance sampling. So we can use importance sampling to correct the distribution. And so there's a paper showing that by using this trick, we can improve the AUC by several %. And now the question is how to calculate this winning probability. So that's the next model I want to talk about, is cost estimation. And in RTB, we have this online auction, which is called second price auction. So here, the bidder with the highest bid will win this auction, but he always pays the second highest bid. And the problem here is that if only the winner knows about the true winning price. So if I lose this auction, then I have no idea how much more I need to bid in order to win. So the challenge here is that we have censored data. And also the bidding environment is highly stochastic. So here, how can we correctly estimate the winning probability? So here is an example. So the left box shows the bidding log. And if we want to, a traditional way or an easy way to say, what's the winning probability if I bid at 3? So if we set the bid price as 3, so we just check here all the impressions we won. So we won 4 auctions. And if I bid 3, then my winning probability would be 70%. But it's not the case, because sometimes when I bid 3 or even I bid 4, I will lose some auctions. So we need to correct this winning probability. So here, survival model is introduced to solve this problem. And another problem here is that, for example, we can use the survival model and then we can correct the winning probability. But we usually use only one model to approximate this market. But let's take a look at this graph here. So if I just select data from Sunday and also some data from Wednesday, and you can see here is that if I bid at a certain price, the winning probabilities are different. So it's not really optimal to use only one model to approximate the winning probability. So one way to do it is that we check all the features, and then we fix one of them, and we take a look at two data sets. For example, here, let's fix the feature value of region. And then we take a look at the market distribution for two subgroups. And we use KLD, KL divergence matrix, to measure the difference between the two distributions. And the higher the KLD is, and the more different the two distributions are. So in this case, we select the feature which can generate the leaf nodes, and we need to make sure like all the nodes here will have distinguishable market price distribution. And in this way, we find subgroups in our data. So when we approximate the winning probability, we will just go through, just look at the features in the bid request, and then go through the decision tree, and then find the leaf node, and use the distribution of that subgroup to calculate the winning rate for that specific bid request. And finally, once we have a user behavior prediction model and the markets model, we can come up with a bidding function. So here, a very simple bidding function used in the second price auction is called truth-telling bidding. Means that you just simply bid the value you believe or you evaluate for each ad impression, which is the cost per click multiplied by the click-through rate. But usually, if you set a bid price like this, it cannot respond to this highly dynamic environment. So usually we don't use truth-telling bidding strategies. We need to adjust the bidding strategy based on our budget and also based on the dynamic market. So here the goal of not truthful bidding strategies would be to maximize the key performance indicator, which could be the number of clicks or the number of conversions. And we need to add a constraint here. We cannot spend beyond our budget. So one optimal bidding function is proposed by just translate this goal into this equation. So first we receive a bid request. We represent it as Px. And then we use a CTR model, which is theta x. And we use that CTR to calculate the bid price. And once we have the bid price, we need to calculate the winning probability. And here, NT is the amount of auctions. And in this way, we can directly optimize the bidding function. So we are not trying to optimize any parameter here, but the parameter here we want to optimize is the bidding function itself. And here, there's some dependency assumption, because to work directly on this high-dimensional feature vector is it's really complicated. So we need to simplify this problem. So here we remove the x and only use the CTR theta to represent the dynamic of the bid request. And here, the solution is to use calculus of variance calculus of variations, and we introduce the Lagrangian multiplier. And to solve this, we just take the partial derivative of the bid request of the bidding function and make it to be 0. And then here we also need to have an equation or a representation for the winning probability, and then it can come up with a simple bidding function like this. So C is a constant here. And in this paper, it shows that the optimal bidding function allocates more budget to the requests with lower CTR. So I guess what is happening is that maybe in that data set, the more clicks are generated in this area. So they can bid at a very low price, and they can maximize the total number of clicks. So the decision is totally different from the linear bidding function. And the trend in the industry is also moving towards using reinforcement learning techniques. So here, reinforcement learning is always formalized as a Markov decision process. So here we are at DSP, and once we receive some bid requests from the bidding market, we need to take an action. So the action would be a bid price. And later on, the bidding market will send us the feedback of the user, which is the click, as the reward. So this is the reward we need to optimize, or we need to maximize. And usually, so there's one paper that formalized the RTB problem into a model-based RL. But usually in the model-based RL, it needs the full knowledge of the state transition probability, which means that it needs to know from one state to the other state what's the probability. So here is one example. So if we take, we design this task as an episodic task. For example, we have, let's say, 1,000 auctions per episode, and we reset the budget setting for every 1,000 auctions. And we need to calculate the transition probability. And here, let's just say the state is the number of auctions we have in this episode, and also the budget which is allocated for this episode. And once we have this state, we need to take an action, which is the bid price. And there are two possibilities. One is we win or we lose. So in any case, the number of auctions will be n-1 in the next state. And if we win, the total budget will just subtract the cost of this auction, of this bid. And if we lose, and the budget doesn't change because we don't need to pay anything. So here, we need to calculate the transition probability, which is the winning probability. So once we have it, and then we need to maximize the reward. So when we win this auction, the reward would be the predicted CTR. And if we lost, the reward is 0. So we can use the very classic Bellman equation to solve this problem, and to use dynamic programming to iteratively update the value function, and then derive the action which maximize the value function as the best policy to take. But the limitations here is that first we need to model the environment. We need to guess, to model the winning probability. And also it's not very scalable with larger state space and also with maybe continuous action space. So the trend is that we need to move forward to use model-free reinforcement learning, or we can also use, we can also directly parameterize the policy. So here is just some recent papers published by some big Chinese companies. They use multi-agent reinforcement learning based RTB. So in this case, it's because they have multiple advertisers, so it's really hard to train one model per advertiser. So that's why they make the advertisers to form a number of clusters, and for one cluster they can train a policy. And let's say in this case they have 3 agents, and these agents, they can set a common goal to achieve, or they can also set their objective separately. So in this way, when they work in coordinate way, so the agent, one of the agents, it can generate a lot of profits. So it will, so this agent will always bid or represent for this DSP. The other 2 agents will bid less, but their total goal is achieved because they have they generate more profits. In the other setting, when each agent only cares about their own profit, and you can see that they try to maximize their own profit, and the total profit for this DSP is not maximized. So I think right now, deep reinforcement learning technique is being widely studied by the industry and also by the academia. And personally, my research interest also relies in using reinforcement learning-based technique to design real-time bidding functions. And of course, there are many more research topics in this area. For example, today I only explained the models being used by the advertisers. But on the publisher's side, they also need to set some price to maximize their revenue. And also, we can see some ad frauds, because maybe some websites, they just generate clicks automatically, which will take advertisers' money, but there's no profits generated because no one will actually buy anything. So in this area, you can also work on ad fraud detection. So, and of course, the topics are not limited to the ones I listed here. So you can find a lot more interesting problems in this area, I think. And that summarizes today's talk. And thank you for your attention. Yes.
Yeah, and I noticed, so you're saying that there's a conflict of interest between these DSPs and the advertisers, because there would be potentially the clients of theirs that would be undervalued, that would be assigned the wrong policy because DSPs wants to help them sort the profit as high as possible.
So you're saying, like, if a DSP and their customer, the advertisers, have conflict objectives. I guess it depends. I mean, I think for the advertisers, so each one of them, they have their own goal, and the DSP needs to fulfill their goal as well, I think. So
the end, if they are unsatisfied, they will leave, and then they won't make any money.
yeah, I guess.
One question regarding like how stable you assume this winning distribution, for example, because I imagine if you're like in an environment that is changing really fast, then you determine like all this your optimal bidding strategy, and by doing that you basically influence the system.
Yeah.
And then did you like have any measures, or did you like figure out, or is there some work on that? Like does it really make sense to do all this effort if the system is so dynamic that anyway it's going to be not optimal?
Okay, so basically you're asking like how often we need to retrain the model.
Yes, and how fast, like, what is the actual optimality that you could achieve, like, in a real market situation with a certain, I don't know how ad market is, but like with a certain size of the market volume or something like that?
So I think for the advertisers, they have their goal is to keep the cost per click as least as possible. So when they have some like criteria, and if they monitor the performance drops, let's say after a day, because they don't change their strategy that often, let's say every seconds or every minutes. So usually they could check it on daily basis and to see if there's the performance drops or improves, and then they can retrain the model.
But do you not think, like, if you would update it on a daily basis, and you would, for example, assume parameters like during a work week, for example, like on the weekend people are looking more often, then this would already interfere with each other, that you cannot really like have a nice confidence on what you're doing from a bidding perspective?
Yes, I think there are a lot of papers, they train the models, because they usually train the models offline, and then they test it online, and to see the actual online performance, because sometimes you, like you said, while you are training the model, you are also like interacting with the environment, and you have an influence, or you have some impact on the environment already. But I mean, usually, let's say during a day or a few days, or let's say a week, it has some changes. But usually, let's say if you use like 1 week data for training, and maybe there are some changes the next day, but still they wouldn't affect the model like too much, or the performance too much. Yes.
It's an observation that leads to a question, but I've seen in your talk that sparse data was clearly a problem, but what I'm quite surprised that you mentioned that you needed to have it high speed, like 100 milliseconds, which includes like networking, retrieving data from elsewhere, pre-processing, and the models. But it seems that you are using more or less the same kind of models or family of solutions that we could find for other problems. So in the end, like the speed and performance doesn't seem to be a big problem, isn't it?
I think because I never tried to apply all the algorithms online. But I think the major efforts, I mean the model training and so on, they are happening always offline anyway. So usually in the online mode, you just need to use this model and quickly get a number and then send it back. There's not so many, let's say, complexity realized in the real time or the online part.
So, no more questions? So let's thank the speaker again. So also thank you from my side for attending, and I want to remind you that we have a YouTube channel now, so please subscribe to our channel if you like the talks that we are streaming, and like give us a thumbs up. I think that's what you say when you do YouTube videos. So thank you.